No. Okay, so we're going to have a potentiometry or potentiometric method starting today. So if you're going to look at the potentiometric method, this is just based on the measurements of the potential on electrochemical cell in the absence of appreciable current. So when you have this method, okay, usually the one that you're measuring here is the potential. So it's a kind of electroanalytical techniques in that the potential difference of a solution between the two electrons is measured with the help of electrochemical cell without drawing any substantial current from the solution components. Okay, so here we could say we need at least 2 electrodes. Okay, they said electrochemistry with 1 electron is just like clapping with 1 hand. So you know you cannot clap with 1 hand, right? So at least in electrochemistry, you need either 2 electrodes, that's for potentiometric methods, or 3 electrodes, that's for the voltammetric electrode. Now, if we're going to look at this potentiometric method, they said the equipment is simple and inexpensive. And this includes a reference electrode, indicator electrode, and the potential measuring device. Okay, so if we're going to look at this, the fourth thing here is what we call the salt bridge. But if we're going to look at the diagram that we have here, okay, so all of them refers to the basic components of your potentiometric method. Okay, so the design that you have is just similar to this one. Okay, so you have here the reference electrode. So if you're going to look at this in the half cell, this is your what we call the reference electrode. So this is independent of the concentration of the analyte or any other ions in the solution. So what does the reference electrode do? Anyone, if you remember? Okay, so if you have what we call the reference electrode, that could be the comparison, or you're measuring the potential with respect to this reference electrode. So if you have a reference electrode, you could say its potential is known, constant, and independent of the analyte. Okay, now the other half cell, that is what? The indicator electrode. Okay, so the indicator electrode that we have here, okay, this is usually immersed in the solution of the analytes, and you develop a potential that is equals to E individual. So as you could going to see here, in addition, the reference electrode is what? The left hand electrode. Okay, so that is, we could say, the indicator electrode would measure the electrode that you have in the solution, the concentration with respect to the reference electrode, and any difference that you have there, that is the potential that you will get. Okay, so if we're going to look at this, the indicator electrode depends on the activity. Okay, so that's where the species of interest is what we call measure. Okay, so its potential is unknown, and the potential would change depending on the activity or concentration of the analyte. So we could say your indicator electrode, its potential depends on the analyte concentration. Okay, now if we're going to look at the other thing, so we have what we call the salt bridge. What does the salt bridge do? Anyone? If you recall,
electron neutrality po, sir.
Electron neutrality. But that's the aspect of, we could say what? Gen Chem. But we discussed about the new role or the deeper role of salt bridge last time. Ano yung role ng salt bridge dito? So if you're going to look at the salt bridge, what it do? Remember the junction? Okay. It just prevents the components of the analyte solution from mixing with those of the reference electron. From mixing with the reference electrode. Okay, and usually what happens when you have the salt bridge, usually there's a potential that develops across the liquid junction at each of the end of the salt bridge. So here we could say the salt bridge is around here. Okay, so that's around this what we call the porous membrane that we have. So there's a potential that developed there, the potential due to this junction potential. So these two potential, the junction potential that you have, they tend to cancel one another if the mobilities of the cation and anion in the salt bridge are what we call the same. So what do you think is the most common or preferred salt that they use?
KCl po.
Okay, so they usually use KCl. That's the nearly ideal electrolyte for the salt bridge because the mobilities of the K plus and the chloride ion are almost equal. Okay, so the net potential that you have there in your what we call the salt bridge, okay, the EJ, as they call it, they are reduced to a few millivolts or less. So we could say the junction potential here is small enough to be neglected. So if you're going to look, okay, at this what we call potentiometric method, so we have the reference electrode, the indicator electrode, the salt bridge. What is the potential measuring device? Anyone? What could that be?
Yung digital meter po, sir.
Digital meter, or that's what we call the potentiometer. Okay, so with the potentiometer or the rheostat, as they call it, usually it has a role there. Okay, so the potentiometer, the rheostat, that's a device that pushes back the current produced in the circuit. So remember, we don't need current in this method. So what the potentiometer, okay, do is pushes back the current produced in the circuit due to the chemical reaction and thus minimize the flow of current in the circuit to avoid, what do you think it avoid? Sa last lesson natin, ano yung cause ng current usually sa electrode? It causes polarization. So what this, what we call potentiometer is it push back the current that is produced in the circuit due to the chemical reaction, and it minimizes the flow of current to avoid the polarization of electrode. It also measures the amount of potential, okay, that is produced at the surface of indicator electrode by comparing the non-potential of the source connected with the potentiometer. That's why you see there what? A number. Okay, so if we're going to look at the potential of the cell that we have here, So we can say that it is equals to what? E cell equals to the E indicator minus the E references. So remember the cell notation that we have. This is your anode on this side. And this is your cathode, right? So E cell is equals to E cathode minus E anode. And then we add what? The potential from the liquid junction. Okay, so we could say here that the potential from the indicator electrode contains the information that we are looking for, which is the concentration of the analyte. So to make a potentiometric measurement or determination of the analyte, we must measure a cell potential, correct this potential for the reference and junction potential, and compute the analyte concentration from the indicator electrode potential. Okay, so strictly speaking, we could say the potential of the galvanic cell is related to the activity of the analyte. So that's, we could say, the basis that we have. And we have to do a proper calibration of the electrode system with the solutions of known concentration that we can determine the concentration of the analyte. Okay, remember, we cannot measure exactly. Okay, we only can have measurements with comparison of known concentration. Okay, I don't know if you notice it, that when you do determination of a certain analyte, you always have what? A standard solution, or we could say a calibration curve. Because in instances like this, you cannot directly measure a certain analyte as it is. You have to compare it with known concentration of analyte. Di ba ganun naman yun? Okay. Have you noticed that in electrochemistry? That's why I like electrochemistry, because you can always have measurement. Hindi kagaya ng organic. You have to prepare or synthesize something and you're not sure if you can get it 100%. That's for me, my, we could say, personal opinion on why I chose analytical chemistry over organic chemistry. Kasi, dyan sa LV, pag organic yung thesis mo, malamang hindi ka graduate on time. I don't know if you're going to agree with that. Tama ba?
Yes po.
Kaya kami nag-opt kami mag-analytical. Kasi kung ano yung measurement, ano magagawa namin? Yun yung measurement eh. Okay? I remember one professor telling my housemate, if you think you can graduate without the reagent, think again. If you think you can graduate without the glass rate, think again. Sagot ng housemate ko, I'll think again, ma'am, if I'm going to get you as advisor. Okay? So that's how we could say in what we call, in any analytical measurement, you always need this what we call standard solution of known concentration and make a comparison doon sa sample mo. So the same thing that is applied here. Okay? So the thing is, the indicator electrode is the one measuring the analyte concentration, but you still have to subtract it with the reference electrode. Kasi isa-subtract mo naman siya sa lahat ng reference electrode, which is the same potential. So the difference there can be kung ano man signal na makukuha mo doon, yun na yun, concentration or signal coming from your target analyte. Okay, now this brings us to the so-called reference electrode. So usually, as I said, you need one electrode of system that acts as a reference electrode against which potential measurement can be made, the relative comparison. Okay, that's why I told you electrochemistry cannot have one electrode. Sabi nga nung dalawang author, if you have electrochemistry with one electrode, it's just like clapping with one hand. Pwede ka ba mag-clap with one hand? Okay, because whenever you do this, what we call electrochemistry, there's always at least a reference electrode and other electrodes to give you the potentiometry. And if you add another electrode, that will give you the voltammetry. Okay. Now, there are, we could say, desired characteristics for this, what we call reference electrode. So the ideal reference electrode has a potential that is known, or we could say constant or fixed, like this one. Okay. And it should have a constant response even when there is a net current in the cell. So even if there's some current in the cell, it will still give you a steady or a constant response. And as much as possible, it is completely insensitive to the composition of solution under study. Okay. And another requirement that you have is it need to obey the so-called Nernstian equation, the Nernst equation. It should has this Nernstian like properties. Okay. It should be reversible. And most importantly, it should be rugged and easy to assemble, and should maintain a constant potential even when there is a net current that I have mentioned there. And you always treat this as your left hand electrode. So there are, we could say, 3 common electrodes used in potentiometry, and we have discussed a lot about this one. So sinet aside ko na to. We discussed about it last time. Okay. So the one that we're going to discuss, although I introduced to you, is the calomel and the silver electrode. Okay. So if we're going to look at this, what we call electrodes, so the most common one are what we call the calomel reference electrode. So this is usually consists of what? Anong metal meron sa calomel electrode? Anyone?
Mercury po.
So you have what we call a mercury. So if you're going to look at this half cell representation, so you have a mercury metal, mercury Cl2 saturated, and you have, we could say, a KCl at a certain concentration. Okay. So if we're going to have that as the half cell reaction, the reaction that we have here would be Hg2Cl2 plus 2 electrode producing Hg, which is liquid, okay, 2 plus 2Cl minus, that is what we call aqueous. Okay, so we could say the half cells of the calomel can be represented by this, and the reaction can, the electrode potential for this half cell can be determined by this given reaction. So it depends on what? If you're going to look at this one, okay? So it depends on the chloride concentration. You put there X, see that, the XM? Okay, that is what we call the response would depend on the concentration of your chloride. So we could say the KCl must be specified if you're using this saturated calomel electrode. Now, the calomel electrode, we could say, is widely used. Why? Because of ease of preparation. Okay, compared with the other, we could say, calomel electrode, its temperature coefficient is larger. Okay, so what does it mean? The equilibration could be slow due to temperature change. So if there's a change in the temperature, hindi agad siya mag-equilibrate. Okay, so it is widely used because it's easy to prepare, but if you have a variable temperature, or temperature is changing, okay, it might take a while for it to equilibrate. Further disadvantages of this is that when the temperature changes, the potential comes to a new value. Okay. And in addition to that, there is what? A leakage of, ano sa tingin niyo mag-leak? KCl. Okay, into the sample, and in addition to that, there is also the possibility of decontamination of mercury. Look at the what we call setup. Although this is less common, especially the mercury one. Okay, but it's still prepared from what we call certain application. But usually right now we want to be what? Environmental friendly. So as much as possible, we don't want to use contamination. Okay. But if you're going to ask superiority of the SCE compared to silver chloride, we could say this is more superior. Compared to the silver chloride. Okay, so that is the SCE. I'm not sure if you're able to see this already in real life. Unfortunately for me, I think I saw it way before. Okay, but the one I use is usually the silver chloride. Kasi ang lab namin, I mean the school namin, pag mercury out agad, inaano agad. Okay, ganun ka OCD yung safety officer namin. Okay, so if you're going to look, okay, at its performance at a certain temperature, so you could see here, depending on the concentration of the KCl. So see what happened. So at 10 degrees, 12 degrees, so you could see at 0.1, the changes happen as the temperature goes up. Okay, so ano nangyayari doon sa reading niya, yung potential. As the temperature goes up, it goes down. Now, if you have it here, okay, so the same thing happened. As the temperature goes up, okay, the potential goes down. I think you observe it in almost all of the electrodes. So if you have a saturated calomel electrode, the same thing. Okay, so as the temperature goes up, the potential goes down. See here how the difference is if you have a saturated calomel electrode. The temperature coefficient is significantly, we could say, larger. So that's the SCE. Okay, so the other one is what we call the silver chloride. So this is the most widely used reference electrode system. So what you have here, a silver electrode immersed in KCl, saturated with silver chloride. Okay, so if you're going to look at this, what we call how you represent this in terms of the cell notation. So you have what? A silver chloride, saturated, and then you have KCl, and then again you have the XM, that one. And in terms of the half cell reaction here, so how do you think it is? Silver chloride plus E producing silver metal and chloride ion. Now, one advantage of this, what we call silver chloride over the SCE is it is useful for temperature above 60 degrees Celsius. So let's see if we see it here. Oh, we didn't show the 60 degrees Celsius. Okay, so the silver electrode, they can have advantage when you use a temperature greater than 60 degrees Celsius. The saturated calomel electrode don't have that capability. Lalo silang magbabago yung potential. Okay? But on the other hand, there's a disadvantage of this one. Silver can react with the ions. Okay? And when that happens, okay, it can lead to what? The plugging of the junction. So mercury ions, they have fewer sample components than the silver ions, which can react with the proteins, for example. So such reaction can lead to the plugging of the junction between the electrode and the analyte solution. Okay? So yun yung disadvantage niya. So, hindi ko na picturean. I have several silver electrode that you have. Okay? And you can, what we call, build a simple potentiometer. You plug a pH meter with a silver wire and then put them together. Okay? And you can, what we call, have a simple potentiometer. I don't know if you still do argentometric reaction. You still do it in, I'm not sure, 32?
Yes po.
Yes po.
So meron pa kayong silver wire na ina-assign or tinatabi nyo sa pH meter? That's
Wala.
wala.
Titrations lang po.
Yun, titration nga. Remember the photo that I show you that contains a lot of pH meter? Okay, so usually those are there because we use them. So maybe on Saturday when the students will do a potentiometric titration, silver ion reacting with halides, I'm going to take a photo. So you will see the setup. Okay. Colorimetric lang kayo, hindi yung monitor yung change in potential, yung parang nagda-drop siya, volume, and then you have potential, tapos yung parang ganon. So ito yung iodide, tapos ito yung chloride. Okay. Wala na, mahal na yung silver eh. Inuuwi ata ng student pagka ano, pagkagamit. Okay? So that's what we call silver chloride electrode. Now, there are some precautions in the use of this so-called reference electrode. Okay? So in using the reference electrode, the level of the internal liquid must always be kept above the level of the liquid in the sample solution. I think I have it here. Okay, so there's a need for you to keep the level of solutions in the reference electrode above the level in the analyte solution to prevent the reaction of the silver or mercury that is there in the reference electrode with the analyte. So you just want to prevent what? Contamination. Because once you have contamination, again, magpa-plug yung junction. Okay? And the plugging of the junction due to the reaction of the analyte solution with silver or mercury from the internal solution. So you need to prevent also the flow of the analyte solution into the reference electrode. Kasi meron tayong tinatawag na junction plugging. So if you're going to look at this one, so yung junction na meron kayo yan. Tapos dito, pwede kayo mag-ano, ito, yung nakadip doon sa analyte. Okay? Walang meters yung ano, wow. So, ang ano nyo lang siguro yung ball hard tsaka more, no? Volumetric method. Yeah, I'll ask some of my students to record. They're doing an experiment this weekend doon sa York. Okay. So when you have this so-called junction plugging, that's the most common problem. Source of error. So that's the most common source of erratic cell behavior in potentiometric measurement. So usually what they do is they put this so-called Bigor plug. So that's what we call some material that they use. Okay, they provide a reproducible low noise junction stop. Okay, to prevent this error. Okay, so those are the precautions that you need to what we call do. So with the liquid level above the analyte solution, some contamination of the sample is inevitable. Okay, so in most instances, the amount of the contamination is too slight to be of concern. So in determining ions such as chloride, potassium, silver, and mercury, however, you have to take some precaution, okay, to avoid this source of error. So a common way is to interpose a second salt bridge between the analyte and the reference electrode. And that bridge should contain non-interfering electrolyte, okay, such as potassium nitrate or sodium sulfate. Why? Bakit itong ginamit? Potassium nitrate or sodium sulfate if you need an additional salt bridge. Most likely, if you have chloride, it can react to produce AgCl and Hg2Cl2. Okay. So that's the precautions that you do in using a reference electrode. Now, question, have you seen what we call a silver chloride electrode? I remember when I went there, I was bringing some of them, I think, and I gave it to Mom Migo, okay? While we're using Dr. Leah Fernando's potentiostat. Okay, so that's the thing that you have to what we call be careful with in using this so-called reference electrode. But as you told me, you're just doing the titration, okay, by volume, not using instruments. So maybe you don't have to be worried of this kind of problem. So this is in terms of this what we call reference electrode, okay? So can result in the plugging of electrode junctions and erratic behavior second salt bridge is using, like non-interfering electrolyte KNO3 and sodium sulfate, okay? Now we go to the other electrode, okay? The so-called indicator electrode. So indicator electrode, we could say, is that electrode whose potential value depends on the concentration of the analyte, okay? And the potential value at its surface usually changes with the change in the concentration of the analyte. So we could say the ideal indicator electrode is the one that responds or detect rapidly and reproducibility, okay? Rapidly and reproducibility to the presence of the analyte or to the changes in the concentration of an analyte of the ion or a group of ion. And there's usually what? 3 common types. The metallic indicator electrodes that involves the one of the first kind, the second kind, the third kind, and the metallic redox indicators. We're going to discuss them one by one, okay? And then we also have the so-called membrane indicator electrodes. So we have here the crystalline membrane electrodes and the non-crystalline. So if you're going to look at this non-crystalline, these are what? The glass one. And then we have the ion selective one, which is the field effect transistor effect. So in the glass electrode, we also have here the so-called the ISE as we go on. So how is it different from this ISE FET? Okay, so let's go to the metallic indicator electrodes. So the first one that we have, the metallic electrodes of the first kind. So what does it mean when you say of the first kind? There's a movie entitled Close Encounters of the Third Kind. Okay. They use it in paranormal thing. So encounter of the first kind, second kind, and third kind. So the same thing with this, what we call metallic indicator electrode. So the way we're going to classify the metallic indicator electrode, there are four main types. So we have the first one, that's the metallic electrode of the first kind. So this is just what? A pure metal that is in direct equilibrium with its cation. Okay. So if you're going to look at the reaction here, so you have X charge plus the number of electron based on the charge producing X solid. Okay. So if you're going to look at this first kind, we could say it involves a single reaction. And the detection of the cathode derived from the metal is used in the electrode. So classic example here is the use of copper electrode to detect copper 2+. So maybe how the reaction looks like. Copper 2+, okay, reacting with 2 electrons to produce copper. Right? So how do you think the potential will get from here? E indicator is just equals to what? The potential of the copper minus 0.0592 divided by 2 log 1 over the activity of the copper 2+. Familiar with that? This is just what? The Nernst equation, right? Or how do you put this activity of copper 2+ that you have here? Maybe you can just put it as the standard cell potential of the copper minus 0.0592 over 2. So this is what? P of copper. So if we're going to write the main equation here, ano yung magiging ano muna dito before we come up with this one? So usually this one, based on this one, log of activity of copper that is solid over activity of copper 2+. And usually, what is the activity of the copper here? We can say it's equals to 1. That's why we put here log of 1 over activity of the copper 2+. So 1 over activity of the copper, we can simplify it by just putting P of copper using P copper equals to negative log of A copper 2 plus. Make sense? Because we say since copper solid here is equals to unity or 1. Now, what's the problem with these electrodes of the first kind? They are not widely used. Okay? Because of what we call several reasons. And one of them is they are not very selective, and they respond not only to their own kind of cations, but also to the other easily reduced cations. Okay? And many of them can be used in only what? Neutral pH. If you're going to use them in the presence of acids, what's the problem? Ano mangyayari pag meron kang metal, nilagyan mo ng acid? You can use it in neutral pH and also basic pH. But if you have the acid, okay, the metal will react. The metal will dissolve in acid, right? Which metal that doesn't dissolve in acid? Anyone? Anong metal ang hindi nag-react sa acid? Anyone? The so-called noble metals. Di ba dyan sa mga tiyangge, para i-ano nyo kung real yung gold, ibabad nyo doon sa suka, or meron sila nilalagay na kalamansi? Meron pa bang ganun? When I was a kid, because I grew up in Mindanao, so there's a lot of traders, yung barter, so sa tabi-tabi. So pag nag-corrode yung jewelry, ang peke yung suka, hindi daw yung jewelry. Okay? But the thing is, if it's a noble metal by the name noble metal, it should not react with the acid. Okay? I don't know if you know the story on how I'm not sure if it's Niels Bohr, how they hide the Nobel medallion, gold medallion that they have. They dissolve it in aquarehia and leave it in a solution, and they recover it after the war. When the Nazi Germany are going to Netherlands, okay, what they did is they don't want it to be confiscated, so they dissolve it. But since gold won't dissolve in acid, they use this aquarehia, okay, a combination of strong acid, if I'm not mistaken, NHO3 and HCl maybe, okay. So you cannot use it in acidic pH. And another thing, okay, it easily oxidizes because it is a metal, okay. So it can only be used when the analyte solutions are what? Paano mo tatanggalin yung oxygen sa solution? You have that in ERG, a tank of that. So, talagang ano ko doon kay ewan ko kilala niyo si Manong Linis, si Manny Linis. Order mo tayo nito, kailangan ko. Nitrogen. So we put some nitrogen so it displays some of the oxygen para hindi mag-react doon sa metal electrode. Okay? So another thing that you can have is some hard metals like Fe, chromium, cobalt, and nickel. They do not provide reproducible potentials. Okay? So they don't provide reproducible potentials. So you cannot have a reading that is different, even though you have the same kind of metal. Okay. And then another thing is you have to what we call, if you have this type of what we call metal, you can make a plot of the concentration of that what we call px versus the activity, okay, and they differ significantly and irregularly from the theoretical. So what is the theoretical there? The 0.0592 over n. So they found out that the plots of px versus activity, they differ significantly and irregularity. Okay, so for this reason, the only metal that is being used for the first kind is the silver ion, and the mercury ion. That's in neutral solution. And then they also use the copper and the copper 2 plus, the zinc and the zinc 2 plus, okay, the cadmium and the cadmium 2 plus, the bismuth and the bismuth 3 plus, ano yung TL? Tantalum, and then the lead and lead 2 plus in what? Deaerated. So, ibig sabihin, kailangan mo ng nitrogen gas. Okay, so that's the what we call metallic orders of the first kind. Now, if we have the metallic order of the first kind, so we can also have the so-called metallic order of the second kind. So here, we have, again, a metal electrode that can be made responsive to the activities of an anion that form sparingly soluble precipitate or stable complexes. Okay, so we could say an example here is the silver electrode. You can make it a metal electrode of the second kind to detect fluoride, okay, or other halide like solution. So what usually happen here? So either you form precipitates or complexes. So here, when you have a silver, okay, so how do you think the reaction here? Silver reacting with what? The chloride, you produce Cl, and then there's an electrode, and what do you have? Silver S and chloride ion. And you have a potential there that is equals to 0.22 volts. Now, if you're going to look at the potential of the indicator electrode here, what would that be? Okay, so if you try to measure the chloride, so you could say the potential that you will get 0.0592 divided by 1, because you only have 1 electrons in chloride, and then you have what? Log of A silver that is solid times A Cl minus over activity of silver chloride solid. And what can we say about the solid here? They are both equals to unity. So this now becomes E indicator, and this having 0.22 volts. So you have 0.0592 over 1, and this becomes what? Log of ACl minus. or we could say that is also equals to 0.22 volts plus, wait, gawin kong plus 0.592 P chloride or chlorine. So you see the difference of the first kind and the second kind. So first kind, we could say direct. Second kind is indirect. So there must be some product that is produced. And another example that we can use here is this one. Ano ba yung anong silver reaction? Yung if chloride is present, you add it with silver chloride. Is it the more or the ball hard? I know there's two types of what we call reaction that you have there. Hindi ko kasi ginagawa kasi I told you we're using instrumental, but if you're using the colorimetric one, that's I think the name, the ball hard and the more method. Okay, so we could say this is like the principle behind that. Now another one would be the detection of EDTA ion with the mercury chloride electrode. Okay, so if you're going to look at the reaction here, so ano sa tingin niyo magre-react dito? Hg Y2 minus plus 2 electrons to produce Hg liquid plus Y4 minus, and the reduction potential that you have there is 0.21 volts. And if you're going to look at the indicator potential that you have there, okay, that responds to the activity of Y4 minus, so this would be equals to what? 0.21 volts minus 0.0592 over 2, and then you have log of what? The activity of Hg liquid, activity of Y4 minus divided by activity of HgY2 minus. And then again, okay, you can put the liquid there as what? This equals to 1. So you end up with 0.21 minus 0.0592 over 2. That's log activity of Y4 minus over activity of HgY2 minus. Now, to use this system, okay, to use this electrode system, you have to introduce a small amount of Hg Y2 minus into the analyte at the outset. And the complex that is formed is so stable that its activity remains essentially constant over a wide range of Y4 minus. So you're familiar with EDTA, right? You're doing
Yes,
it in the determination of what? Hard water?
Yes po, sir.
The calcium and the magnesium thing? Okay. So EDTA is one way to remove if you have a heavy metal contamination, because the complex that formed there is so stable. Okay, but some metal, if you're going to, let's say, which react preferably with the EDTA, so it depends on the Kf value that they have. So when you introduce some of these HgY2 minus into the analyte, you can rewrite the potential equation. So you can say E is equals to K minus 0.0592 over 2, and then this is what log of a Y4 minus. Okay, or you could say your K now is just plus 0.0592 over 2 Py. So the K there, that is the KF. And they found it to be around 6.3 times 10 to the 21. So you can see it's so high. So the forward reaction will be 3 pairs. So it will really form the Hg Y2 minus. Okay. And you can rearrange them that you put what? The K on this side and then put the E 0.21 minus 0.0592. Yung kagaya kanina. So that is, we could say, another example of the second kind. Now the third kind. Now under some circumstance, a metal electrode can be made to respond to a different cation. Okay? And then it then becomes the so-called electrode of a third kind. So if you're able to make this electrode response to a different cation, it's not similar, okay, to the metal, and it doesn't form a precipitate or a complex. But if you can make it respond to a different cation, that's what we call the third kind. So the way you do it, you link it to a cation by an intermediate reaction. So you see the one that we have, the second kind, detection of eta with mercury. So we can make it to detect other cations that bind to eta, affecting the AY4 minus. Okay. And a good example that we have here is what? The mercury electrode used for the determination of calcium containing solutions. And when you do this, you need what? Some eta. A small concentration of the eta complex of mercury 2 is introduced in the solution, and the potential of the mercury electrode in the solutions become like the one that I have shown you. E equals to K minus 0.0592 log AY4 minus, or, okay, we can make it into K plus 0.0592 over 2 P Y. So what happened if you have this, what we call third kind? So a small addition, a small volume of a solution containing the eta complex of calcium is introduced, a new equilibrium is established. So remember, in the determination of hard water, you react eta, okay, with the hard water component, which is a calcium and magnesium. So if you're going to introduce it with calcium, so there's what we call a reaction that is happening here. So what is the K here? If we have this, what we call equilibrium concentration. Activity of the products over activity of the reactant. So if you have here the potential of the indicators, so that's K minus 0.0592 over 2, and then you put the log of Kf times ACA Y2 minus over ACA2 plus. So we could put here that your A Y4 minus is equals to Kf times ACaY2 minus over Ca2 plus. So we just replace the expression here of AY4 minus with this one. And then if we continue, we will have what? 0.0592 over 2 log of Kf ACaY2 minus 0.0592 over 2 log of 1 over a Ca2 plus. And if there's a constant amount of the calcium Y2 minus is used in the analyte solution, and in the solutions for standardizations, we may now write this K prime minus 0.0592 over 2 PCA, where K is just equals to K minus 0.0592 over 2 times log of Kf ACaY2 minus. So we could say the mercury electrode becomes an electrode of the third kind for the calcium ion. So that is the electrode of the third kind. You use a mercury electrode to detect calcium. Questions so far? Nandiyan pa kayo?
Yes po.
Malamig dito ngayon. So the last kind of these so-called metallic indicator electrodes. So these are the metallic redox indicators. So these are the one that is made up from inert metals. So you have the platinum, the gold, and the palladium. So we could say these are the one more expensive than the silver. Okay. So these are electron passion from platinum, gold, palladium, or other inert metals. They often serve as your indicator electrodes for oxidation reaction system. So in a voltammetric system that has 3 electrodes, usually the third electrode that they have is a platinum. That's the indicator electrode. Or the other term that they will have there when we go there is the auxiliary electrode. You bind it with a reference electrode and a working electrode. Now, in a potentiometric system, this indicator electrode, you can also call it what? Your working electrode. Why? Because that's the one that is used to detect your target analyte. Yung tinatawag nating indicator electrode. So, for wording, in some book, they said, potentiometric method, they use a reference electrode and a working electrode. That working electrode is your indicator electrode. Now, in the voltammetric method, they have a reference electrode, a working electrode. Doon sa paper na isusulat nyo, ang working electrode doon ay yung modified carbon phase electrode. And they have a third system that is an auxiliary electrode. And usually the auxiliary electrode are the indicator electrode that they're mentioning here. Okay? So in this, we could say application, the inert electrode act as an electron source or sink for electrons transfer, okay, from a redox system in a given solution. And the classic example that you have here is in detecting Ce3 plus with the platinum electrode. So usually you have here like a reaction of Ce and Ce4, the Ce3 plus and the Ce4 plus. So if you're going to look at the reaction that you have here, so the potential of the indicator electrode, that's the potential minus 0.0592. Since there's only one electrons involved, so you can put here Ce3 plus over Ce4 plus. So the reaction that they have, Ce4 plus electron producing Ce3 plus. So you have there a platinum electrode that serves as the indicator electrode in titration, in which Ce4 plus serves as the standard reagent. So if we're going to look at this, what we call thing here, there are problems that we have in this so-called metallic electrode. Okay. So the electron transfer, the process at what we call inert electrode, they are unfortunately not reversible. So what does it mean? Like the name of the band, one direction. So what happened here is it does not respond predictably to the half reactions in the electrode potential table. Okay. So the example that they put here, if you have a platinum electrode that is immersed in a solution of thiosulfate, so what's the formula for thiosulfate? Okay, so there's a solution of thiosulfate and tetrathionate. SCN, di ba thiocyanide naman yun? So if you have what we call a reaction of this one, S4O6 2 minus plus 2 electrons producing S2O3 2 minus. Okay, so there's an electron transfer process here. So it doesn't exhibit a reproducible potential. Because they found out that the process is slow and one direction, or what we call not reversible. Diba? Ginagamit nyo ba yung one direction when you're teaching equilibrium? When I introduce that, as of now, the reaction that you have is just like the name of the band, one direction. But in reality, most reactions are reversible. So that is what we call the metallic indicator electrode. Okay, so this brings us to the next type, which is the membrane indicator electrodes. So if we have this membrane indicator electrode, there's a wide variety of this what we call membrane indicated electrodes. Okay, and I think they are the one that is commonly available, commercially available. Okay, so they permit the selective and rapid determination of numerous cations and anions by direct potentiometric method. So based on the determination of cations and anions by the selective absorption of these ions to a membrane surface. And we call them the ISE, the ion selective electrodes, or the way they call it is the p-ion electrodes. So ano yung pinakasikat dito? The pH meter. May pH meter ba tayo dyan?
Minsan po.
Minsan po. Wala ako tubig ah. So helpful pag dinekpat ko yung nandoon. What do you mean wala? KCL lang yun, wala kayong KCL? Wala kayong KCL sa lab?
Yung mga standard solutions po, sir.
Oo, mahal yun. Naku, patay ka. Siguro in a month, may darating na fluoride electrode dyan. So bahala na kayo sa fluoride standards. Pinaano ko kay Sir Mix na ibigay kay Ma'am Ami. Okay. So hopefully dumating yung isang lata nung maliit na tsokolate para sa inyo. Yun yung instruction ko. Kasi nagtanong, kanino ko ibibigay ito? Sabi ko, pagdating na, saka ko sabihin. So, if you're going to look at this membrane indicator electrodes or the so-called ISE. So the general mechanism that we have here, so when we say ISE, so we could say the P calcium, the pH, the PNO3. So this is really, we could say, or the one that I sent, PF, specific for a particular analyte. So the general mechanism by which an ion selective potential develops in these devices depend on the nature of the membrane and is entirely different from the source of potential in the metallic indicator electrodes. So here we could say, we have seen that the potential of a metallic electrode arises from the tendency of a redox reaction to occur at an electrode system or surface. But here in membrane electrodes, in contrast, the observed potential is kind of what? A junction potential that develops across a membrane. So some metallic electrodes that we discuss, there's a redox reaction that occur at the surface. But here, what happened? Okay, there's a junction potential that develops across a membrane that separates the analyte solution from the reference solution. Okay, so yun yung pagkakaiba ng membrane indicator electrodes compared doon sa metallic electrodes that we discussed. So walang redox dito. Okay, there's just some sort of a gradient that leads to a junction potential. And there are, we could say, three desired properties of the ion selective membranes, membranes. Okay, so they share these three common properties, which leads to the sensitivity and selectivity of membrane electrode towards certain cations and anions. So the first one is what? Minimal solubility. Ayaw mo naman pag mineasure mo yung, ginamit mo yung ISE mo, mineasure mo sa sample mo, matutunaw siya or soluble siya. Okay, so as much as possible, you want a membrane that will not dissolve in solution during measurement, right? Make sense? So usually many membranes are formed usually from large molecule or molecular aggregates like what? The silica glasses, the resin, or low-soluble inorganic compounds. Maybe the silver halide, Okay, that can be used as what we call membrane. So that's a necessary property of an ion selective medium. Okay, is its solubility in the analyzed solution. So usually zero solubility. So that's the first, we could say, characteristic or properties. The second one is electrical conductivity. So generally, a membrane must exhibit some electrical conductivity, even though it's small. Okay, so generally this conduction takes the form of migration of the singly charged ion. So remember the different process: migration, convection, ano isa? Diffusion. So here, there should be some sort of migration. Okay, so conduction takes the form of migration of singly charged ion within the membrane. And the third one, there's a selective reactivity with the analyte. So a membrane or some species contained within the membrane matrix must be capable of selectively binding the analyte ion. So anong type ng binding or reaction? Not really reaction, like interaction do you have here? Paano siya magiging selective? So it's just doon sa binigay kong paper sa inyo, mga thesis sa inyo, there are some properties of the modifiers that allow it to interact with the target analyte, which in that case are the metals, specifically lead. So the same thing here. Okay, so a membrane or some species within the membrane matrix must be capable of selectively binding the analyte ion. So these types of binding can be what? Obviously, ito yung number one, because you interact with ions. Okay, and then what else? Crystallization and complexation. The former two, okay, are the more common. And we will largely focus on this type of bindings. No oras na ba? Kaya pa ba? So those are, we could say, the three desirable properties that you have in ion selective electrode membrane. Okay, so maybe this is the one that I'll stop. So have you experienced measuring pH using these two type of pH meter? Or yung isa lang ang na-experience nyo? Yung pen type lang? Or yung pang-aquarium lang? Yeah, hassle kasi itong dalawa eh. Masikip sa beaker. Okay? Compared to what we call yung isahan lang. But usually, what you have there is makikita nyo na yung tinatawag na glass electrode at yung tinatawag na combination probe. So ito yung combination probe. Ito yung glass electrode. So the pH electrode, that's the most common example of ISE. Siguro naman may experience na kayong gumamit nito, no? Yung totoo, maawa naman ako sa inyo. Parang yung isang ahead sa akin na PhD student. Ang galing daw niyang gumamit ng pH meter. Tapos maya-maya nag-o-order at basag lagi. Tapos pina-check sa akin ng advisor bakit nababasag. Sa tingin nyo, anong ginagawa niya? Binababa niya yung probe tapos tinatamaan ng magnetic stirrer. Kaya basag. Kaya wala akong believe doon sa lahi nun eh. Ayaw ko lang sabihin. Pag alam niyo yung kanta na may pana, yun na yun. Okay? Kasi nakasulat sa CV niya nung pumasok sa grad school, knows how to use everything. So, we have what we call a glass electrode here. So you have an indicator electrode, which is this one, and a reference electrode. This is a saturated calomel electrode, and they are immersed in a solution of unknown pH. So the typical pH electrode system, you can have what? Two reference electrodes here. One that is SCE. So usually the SCE is what? Outside of membrane. And one that has a silver chloride, so SCE, outside membrane. And the silver chloride, that is, we could say, inside membrane. And what do you think is the pH sensing element? Usually yung glass tip. Glass tip ng silver chloride. Now, if you have a combination probe, so this is consisting of both the indicator glass electrode and a silver reference electrode, silver chloride reference electrode. So I still when I arrived, I think in 2011 in your college, they still do this one. Kaso hassle. And then when the boss asked me to order, ito yung mga in-order ko. Kasi yung student, hindi rin nila alam masyado ano eh. Tapos sabi ko, pag nabasag yan, isa, sila agad. So at least we find this one. And there are some that is what we call the sturdy type. Parang pen type lang. Okay. That's why you could see there's a lot of equipment doon sa school na yun. Kung madugas lang ako, ang dami ko nakuhang mga instrument doon gaya ng pH meter. Okay, so I think I'll stop here. Okay, and then do you have any question doon sa gagawin ninyo? I think I already got the timetable. We have until January, right? Although the end of class is what? December 21, if I'm not mistaken. May pinos eh. Nagre-record ka, Carmel? Sa Wish Radio Station? Anuhin mo yung parody ng Uhaw or Wow ni Michael B.
Sir, alin po yung until January po? Yung review paper lang po.
Oo, yung isusulat nyo. Pero if you can finish ahead, much better. Kung gusto nyo ma-max yung 1.
December 21 po yung end of class.
Oo, pero mag-aano tayo na meron tayong final exam.
Ayos po.
Off record ko lang.